Alright. So our problem was question 3. Oil is leaking from a pipeline on the surface of a lake and forms an oil slick whose volume increases at a constant rate of 2,000 cubic centimeters per minute. The oil leak takes the form of the right circular cylinder with both its radius and height changing with time. Note the volume V of the right circular cylinder with radius r and height h is given by V equals pi r squared h. Then our first problem is A. At the instant when the radius of the oil slick is 100 centimeters and the height is 0.5 centimeters, the radius is increasing at a rate of 2.5 centimeters per minute. At this instant, what is the rate of change of the height of the oil slick with respect to time, in centimeters per minute?
Okay, so for A, first we wrote down the variables, which is dV over dt would be 2,000 centimeters cubed per minute, and dr over dt, which is 2.5. And then we used input differentiation to find the rate of change. And then we got 0.038 centimeters per minute.
Does everyone understand where they got these numbers from exactly? Okay, that's exactly what they listed first. Then they took the equation and actually solved for the derivative. They plugged everything back in, and the rate at which the height changes is 0.03 centimeters per minute, which they also got. Now, they put the rate at which the volume changes and the rate at which the radius changes, which was 1 point. The expression itself for the derivative of the volume counts for 2 points because of both separate parts, which include the derivative of the rate while adding the derivative of the height. And then they get another point for answering the correct answer, which so far they have 4 points.
So for part B, a recovery device arrives on the scene and begins removing oil. The rate at which oil is removed is R of T equals 400 square root of T cubic centimeters per minute, where T is the time in minutes since the device began working. Oil continues to leak at a rate of 2,000 cubic centimeters per minute. Find the time T when the oil slick reaches its maximum volume. Justify your answer.
So we have dV over dt equal to 2,000 minus R of T. R of T is 400 with times to the square root of T. And with T equal 25, we have 2,000 minus 2,000, make it easy to 0. Now we have dV over dt equals 0. That's the critical point, and we check both sides. So when 0 is less than T and T is less than 25, dV dt is greater than 0. And when T is greater than 25, dV dt is less than 0. So which means there's a maximum.
Alright, so once again, reviewing their answer, what they plugged in, they solved for R of T, which is equal to 200. They have the correct answer, and they have the proper justification because they found when D of E is greater than 0, for which 0 is less than T, but is less than 25. And the derivative is less than 0 for T is greater than 25, which everything so far checks out. They've got 3 out of 3 points. In total, they have 7 out of 9 so far.
Okay, for C. By the time the recovery device began removing oil, 60,000 cubic centimeters of oil had already leaked. Right, but do not evaluate an expression involving an integral that gives the volume of oil at the time found in part B.
So 60,000 is initials. The initials oil that have been leaked, and this from 0 to 25, so it becomes from 0 to 25. There's the maximum is 25, so 0 to 25 is decreasing the leaking, so we have 2,000 minus RT dt. For 6,000 is equal to the leaking.
We don't have to do that.
Yeah, all you have to do is write the integral. So you have to, so far all you had to do was actually just break it down, in which it was the 2 parts, the 60,000 plus the integral. The The 60,000 was a number by itself different because given by at problem C, and yet the integral was also given, and they just had to match those up together. So yeah, you guys actually have it. You might not have learned. Not stuck at the teacher I know.
Good job, Monica.